Alright, continuing on with the main concepts of Chapter 5. So, this arguably is one of the most important concepts in this chapter. You'll be using this for the rest of the year, and not only that, but when you take the AP exam, in the free response section, you'll be asked at least once, if not more, to draw a free body diagram. They'll usually break the question up into multiple parts, and one of the parts will be just draw a free body diagram of the situation. So you're going to see a bunch of examples of me doing a free body diagram in the sample problems. So here I'll just tell you what needs to be in it. So you'll either be presented, like on an AP exam, with a dot. Oops. Dot. Or a box, usually. I like to draw a box representing the object, irregardless of what type of object it is. If it's a car, I draw a box. If it's a cow, I draw a box. If it's your mom, if it's sorry, I didn't say that. But sometimes you'll see a dot, which to me represents the center of the box, because you draw the free body diagram force vectors from the center of the block or from the dot. So for example, let's say this is an object on a table. So let's draw the real picture of it. So let's say we got just a box on the floor being pulled by a rope, and there's friction. Alright, so there's friction here. There's a rope. Yeah. So let me do the box example, realizing that I could draw the same thing. Well, let me just actually put the dot in the center and do the best of both worlds. That's cool. Alright. So first thing is, if possible, try to draw the force vectors to scale. I didn't give enough information in this problem for you to know the scale, but there are a couple things you do know. If it's on a surface, like a floor, then it's not accelerating up or down. So you know that the normal force from the floor must equal the force of gravity pulling it down. And we haven't really talked about normal force yet, what it is, so I'll explain it as I draw. But let's say the force of gravity is like that big. Then the normal force would be equal and pointing up, force normal. So normal force comes from the word normal, which in math anyway means perpendicular. It's perpendicular to a surface, and it's the force that the surface exerts on an object. So here the surface is the floor, and if the floor is horizontal, then perpendicular to that is vertical. And the floor is pushing up on the block to counteract gravity. That's a normal force. You can have a normal force on a wall. If you have a wall and you're pushing a block against the wall, the normal force of the wall against the block is that way. If you have a block on a ramp, the surface is this way, so perpendicular to that is that way. So that's the direction of the normal force. So that's kind of what a normal force is. Then we got a rope, which gives a tension. So we have a tension force going that way. And again, I didn't say anything about how big it was. I didn't say whether this was accelerating, whether the net force in the horizontal direction was 0. But we do not know, hopefully through intuition or through experience, that friction slows things down. So if we're pulling to the right, then friction will be acting to the left to slow it down. Let's just say it's not as big as the tension force. So this is one example of a free body diagram. You can see I got all the forces coming from the center. They're to scale as much as possible. They're labeled with their arrows, so they're force vectors. They're labeled with the type of force. You could even write the whole word out: normal, tension, gravity, but usually just a little abbreviation like this is enough. You don't draw any other objects. So you don't draw the ground, you don't draw anything, you don't draw the rope, you don't draw anything interacting with it, just the forces and the object. There might be another block on here. If that's the case, there's another force. This block would be pushing down with it's a normal force in a sense because it's the surface here. But you could say if this is block 1 and this is block 2, you could say the force of block 1, F. Well, that's kind of hard to see. F1 going down, but I don't draw block 1. And not only that, it's pretty obvious that block 2 is pushing up on block 1. So this is the force of block 2 on block 1, right? So what's keeping up block 1? It's block 2 pushing up. But I don't draw this F2 force going up because that's acting on block 1. This is block 2 here. So only the forces drawn are acting on the object. I probably should have written those out, but hopefully you're taking notes on those as I go. And that's pretty much it for free body diagram in terms of stipulations. So let me just pause it and then I'll write them out. I don't want to waste time on the video writing them, and then you can write them down. You can pause it yourself and write it down. Okay, that ought to do it. Once you pause the video, if you want to write these down, and then hit play when you're done. I'm going to move on, starting now. Alright, tension in an ideal rope, no mess or stretch, is the same all along the rope. So what does that mean? Oops. For example, let's say we have ground, ground, and a block here, and a block here, and a rope connecting them, and let's say there's a handle here and someone's pulling this, pulling it that way. Well, if they're pulling it, then you know that the rope is going to be taut, T-A-U-T, right? I think that's right. Meaning like stiff or pulled tight, or there's tension in the rope. And this rope is going to drag along this box. Well, let's do a free body diagram of this block right here, down here. Now remember, we only draw the object and only the forces acting on that object. So we got F pull, not pun, pull. Of course we got FG, which equals Fn, and then we got Ft. Let's assume that the surface has no friction, so we don't have to draw the friction force. Of course, you know the friction force will be going this way as well. What concept 6 is saying is that if I were to draw the free body diagram of this backwards block here, we got Fg and Fn, and those are equal. Then we got Ft from the rope pulling that way. All it's saying is this tension equals this tension. The force of tension all throughout the rope is the same. So the tension here is the same as the tension here, same as the tension here. So when you draw a free body diagram, that's often a way to link the two objects. You know that this tension and this tension are equal. Another way of showing that, if you have a ramp here, and say there's a little pulley at the top, like here, pulley. You have a block here on the ramp and a rope wrapped around the pulley to a hanging mass. You know the tension going up this way, holding this block up or pulling this block up, equals the tension pulling this block up the ramp, because the tension in the rope, even with the pulley attached, is equal all throughout. That's only with an ideal rope, which means it doesn't really exist. It's a rope that has no mass and doesn't stretch or do anything else. It's like a purely solid object. Uh, Geometry of net forces on a ramp. Alright, see if I can do this in the last 5 minutes. Is this the last one? Yes. Oh, I missed one. I'm gonna actually put these last two, sorry I skipped one, last two in a different video because they're both kind of long. So we'll stop here at concept 6.